Ladies and gentlemen, welcome to the first chapter, Balances on Various Length Scales. So the good point here in using blended learning is that if you watch this video, of course, you can choose a faster velocity in playing it. So balances on various length scales, of course, all of you should know that there are different sizes of control volumes. Possible. So a control volume, of course, is just abbreviated by using CV. So different sizes of control volumes are possible for everything that we need. So that is mass, momentum, heat, total energy, species, linear momentum, and whatever. Okay, so if I look at a certain case, so you have a vessel, you have an inflow mass fraction or mass flux and an outflow mass flux. You have some electric power for the pump. You have some heat flux, Q dot, and a heat exchanger. And everything here, of course, is maybe a problem that you want to look at. And now, of course, you can choose different control volumes in the different scales. So the first one would be, for example, here, you just choose, oh no, just like, let's take another point. Let's take here something, a pump. Let's say here on the pump, you want to have a look at the cavitation that may occur, something like that. So you have a molecular length scale and the characteristic size is about several angstroms. So that means that your control volume has only several molecules, and that means that your balancers would be formulated of course only for the interaction. So that means the balancers should be formulated for the forces or force potentials, and that for each molecule. Okay, so that's a completely different approach than we are usually using. Usually, this approach or this length scale is chosen by physicists. So here, you can use this approach to fundamentally research the fluid structure. So that means, for example, what happens with the molecules if you have a cavitation bubble at some plate of the pump, and what do you see there in the wetting properties or something like that. Of course, you can do that very well by using molecular length scale, because then you have your forces and potential of the molecules belonging to the gas phase, to the fluid phase, and also to the solid phase. And here, all molecules have a certain velocity. And if we use this certain velocity and average it. So we are using an averaging process. That would mean, of course, that we have to choose a control volume that is somewhat greater than this one for the molecular length scale. Then, by the averaging process, we get the properties for the temperature, the pressure, the mean velocity, so the macroscopic velocity. Why doesn't it work? Okay, no, it works. So V, which is a vector, and also the some parameters like the kinematic or dynamic viscosity. So then if we use the molecules in a greater control volume and do the averaging process, we end up at the continuum mechanics. But of course, if we are choosing another length scale, which is now as after averaging, of course, in a greater control volume, we are leaving the molecular length scale, then we have a different length scale. And in the continuum mechanics, we lose of what is happening to the molecules, fluid structure, and so on. So we do not have a region in which the phases change, for example, from fluid to gaseous phase. But in the continuum mechanics, we have a free interface. And on the one side, we have a fluid or liquid, and on the other side, we have a gas. Okay, so then, of course, we lose everything that happens in small structures of the fluid, for example, like in the interface or the phase change region. Okay, so that means that if we're leaving the molecular scale, then we're entering, now let's take another color, then we are entering, which is part B, the microscopic scale. For the microscopic scale, we usually take a very small arbitrary volume, which of course all of you know. So this one here would be a microscopic scale. In the microscopic scale, we have a infinitesimally small control volume, and we only also have a infinitesimally balance. So that means that here we have a lot of molecules in the control volume, so we can use continuum mechanics. Of course, we lose something, we lose informations about the fluid structures, but also, of course, we have some advantages in using a microscopic length scale, which is that we can formulate differential equations of conservation of mass, momentum, heat, total energy, species, turbulent energy, whatever. And all the stuff here are, of course, the well-known transport equations. And Now with those transport equations, of course, we can look at what is happening inside the vessel. So if we have in our problem spatial gradients, then we additionally need some boundary conditions. Radiation is BC. And if we have transient gradients, then of course we need initial conditions. So the ICs. Yeah. And then if we have the transport equations and the boundary conditions and initial conditions, we can solve our partial differential equations, which are the transport equations, solving the PDE system. And then we get detailed informations what is happening inside all components. So that means if we're dealing with the microscopic length scale and the transport equations, we get the scalar or vector fields of the velocity, the pressure, temperature, and whatever. That means that here in my control volume, again, if I make my control volume greater and expand it and include the boundary conditions and the initial conditions, then I will go to the integral balance. And then again, of course, I will lose some information. And the loss of information is here the loss of what is happening inside the flow. So if I make my control volume greater starting from a molecular length scale, then I will lose everything about the fluid structure. But then I do not still no longer have certain velocities of molecules, but I get continuum mechanics properties like temperature, pressure, velocity, and so on. And if then then I am in the length scale of the microscopic length scale, and then I get informations about what is happening inside the flow. So how does the fluid flow, for example? And I also need my boundary conditions and initial conditions in order to get the real solution. And if then I am not very interested about what is happening really inside the flow, I can also again extend my control volume and include my whole system. Okay, and then I am at the macroscopic length scale. And if I'm doing that, of course, again, I will lose information, and that is what is happening inside the flow. And that is the third length scale, which I will talk about. It is the macroscopic length scale. So here I have the integral balances. So let's take the sketch again. So the integral balance would be if my control volume would look like this. Okay, then the whole system would be a part of my control volume. And then, of course, here I would have my mass fluxes leaving and entering my control volume, the electric power supplied to the pump, as well as the heat flux of the heat exchanger. So then, if I am in the macroscopic scale, I can use the integral balances, which means that the entire vessel is the control volume, CB of course, and integral fluxes for mass, momentum, and so on is what I can use. And the benefit in doing so is that I do not need informations, detailed informations inside the vessel. And also, that's the drawback, then of course, we do not get informations. About what's happening inside the vessel. So, for example, what's happening inside the pipe, the pump, or whatever. So, of course, we see that as engineers, if we want to have a look at the system at itself, we have to use the macroscopic length scale. That makes most sense. If we want to optimize the flow inside a vessel or a reactor, a pump, or whatever, then of course the macroscopic length scale doesn't make any sense because we do not get detailed information about what's happening on the length scale that we're interested in. Therefore, if we want to optimize something, so not the complete system, of course, but if we want to optimize a reactor or something like that, then we have to look at the microscopic scale. But that makes most sense. We cannot have a look at the molecular length scale because we are only able to look at several 10,000 molecules. More is more or less not possible. And yeah, that doesn't, of course, not make any sense to simulate what is happening inside a chemical reactor or something like that. So if we want to optimize something, then we have to choose the microscopic length scale. Okay, so that is the beginning, and that was the short introduction to the length scales.